And just to connect with a lot of folks in the Nighttime Lights community. It's very, very exciting. Around the world, over recent years, there has been a dramatic increase in rates of energy access. In India, they have electrified 100,000 villages in the last decade. That means there are some 300 million more people connected to the grid. That's a remarkable accomplishment. Yet at the same time, India continues to suffer from abysmal power quality. In one study, it was reported that Delhi experienced 1,000 power outages in just a single month. Now, those are not problems that are unique to India. Reliability problems remain stubborn in much of the world. Ghana has gone through a period of an extreme power crisis that lasted years. South Africa continues to struggle with power outages. And of course, we're all reading in the news about power outages in Texas, probably one of the last places on earth that expected to have to deal with these issues. Poor reliability is a constraint on economic growth and development, and it has serious implications for the climate. Yet at the same time, despite its importance, we continue to lack reliable data on access and the stability of power supply in much of the world. For much of the last decade, we have been working with the World Bank to develop new methods to exploit the full set of data available in the Nighttime Lights series to develop new high-resolution electricity access indicators. Many of you, all of you, in fact, are familiar with these Nighttime Lights composites. Here is a composite for Kenya. What our team has endeavored to do is to go deeper than the annual composites and move all the way down to the original nightly data. It's from the nightly data that we can then extract time series on variability and light output. That information is then overlaid on top of additional data that is increasingly available. I saw 𝗖់់ 𝗨𝘀 present earlier today, and so this is a nice follow-on to the work that he and his team have been doing. We also have taken advantage of new high-resolution data on human settlements. This is computer vision-derived data that identifies the location of every building within a country. And if you know the location of built structures, then you can overlay that on top of the Nighttime Lights time series to develop even more refined indicators of access that are highly spatially specific. And so if we zoom into a portion of Kenya, there's a daytime night image, and in pink, you will see identified what the Facebook computer algorithms identify as the location of a building. And so for each of these pixels, we take it as our task to classify each pixel according to the likelihood of access, and it's an estimate of reliability. And so we generate new data that looks something like this, that generates a continuous measure of the likelihood that we believe that that settlement has access to electricity. Now, these access indicators and reliability indicators come from a nightly comparison of nighttime light data. And so this is not using any composite product, but actually going back to the original nightly time series that goes back for years, back to early 2012, and extends to the present. That is then a remarkable historical record of hundreds of nights of data that both tell us what the light signatures look like over electrified areas and what it looks like over areas that are not only not electrified, but have no settlements. It ends up that by incorporating the full portion of data available within a country, we can identify and extract even more useful knowledge. The general principle of our HREA approach is to compare on every single night. So within every night, we look at the imagery, separate out settlement pixels from non-settlement pixels, and then engage in a matching exercise where for every pixel that it has a settlement, we compare the level of light output to a set of matched unpopulated pixels that have the same land cover and are captured on the same night. Now, the advantage of this is that it controls for other factors that we know are important contributors to light emission detected by the 𝗲 satellite. In particular, lunar illumination and its interaction with land cover. And so I'm in Michigan. If I look out my window as I did last night, you almost don't need any lights on outside to be able to see around, because the moon is, because there's moonlight, and because we've had a recent snowfall. And so snowfall areas have high reflectivity, as do certain types of desert and other types of land cover. Controlling for all of that, then, each night we're able to derive an estimate of the statistical likelihood that a settlement pixel has higher light output than unpopulated pixels. That then gives us a statistical estimate each night, which we can aggregate across the calendar year. This is a zoomed in sense of what that output looks like. So here is an area just outside of Nairobi in which, using that full time series across 2017, we can identify not only the areas that appear to have very high and very stable light output across the calendar time series, but and not only areas that have a very low likelihood of having any access to electricity, because we never see light output in those regions, but we also identify a large number of settlements that fall into this middle range, which maps on very well to what we are increasingly understanding about energy access around the world, that this is not a binary phenomena, but that homes enjoy different levels of access that are impacted both by reliability and also by low levels of usage. And so we generate this type of data across a large number of countries around the world. Now we can work hard, we have worked hard to ground truth and kind of do our best to test the validity of our estimates. And so here's one comparison in which we compare on top our satellite-derived HREA estimates with some ground-based surveys that were conducted several years ago by a team at Berkeley, in which they went door to door and identified homes that had access and did not have access in a part of Kenya. And in this direct comparison, you can see in panel A, for example, that our estimates identify high likelihood of electricity access right by the water's edge. And that's exactly the same pattern that was detected in the ground-based surveys. Panel B finds a similar type of comparison as well. And so some of the village level and household by household level comparisons have produced some very encouraging results. But we can also compare more globally across the country. If we take all of our statistical estimates and aggregate them up, we can generate estimates of the electrification access rate at the country level. And compare that with what is, for now, the best available data, which is reported in the 𝗖cie for all reports at the World Bank. And so on the y-axis are our World Bank estimates. On the x-axis are our HREA estimates for this first batch of countries for which we compared 33 countries over 5 years. The correlation is so high that, in fact, just looking at this scatter plot, you wouldn't be sure which data was based on ground truth, which data was estimated. And just to underscore the point, while surveys are laboriously collected, the satellite-based estimates are automated. And in fact, we have the ability to generate more frequent and more regularly updated satellite-based data than is possible by surveys. We are, in fact, working right now on computing estimates all the way up through 2020. We have launched a pilot of our HREA data, which is now accessible and publicly available. And so I encourage you to visit this website. You can also find the link on my personal web page if you just search for my name. We have now shared HREA data annually across the time frame for which we have VIIRS data for about 25 countries, and we expect to continue to add HREA data for many countries around the world. So I invite you to explore this website. Lastly, let me actually point you to something that may be of even broader interest and excitement to this community. If you have not yet seen the announcements very recently, in fact, just a few weeks ago, in collaboration with the World Bank, we launched the Light Every Night dataset, which is the complete archive of original nightly data collected from the VIIRS day-night band sensor. It also includes every raw nightly image collected from the DMSPOLS sensors. This is data that NOAA has produced over the decades, and in theory has been open access and in the public domain. But up until this point, it has always been a challenge to gain access to the original nightly images. It's always required some customized data pulls by staff at NOAA. But we're grateful for our collaboration with AWS, which has agreed to publish the data on its open data sets program. And so all of this data is now accessible and available. I'll encourage you all to begin exploring it as well. It is a massive data archive. It's about 250 terabytes, which we believe is the largest single access point that provides access to all of the nighttime lights data. And so with that, thank you very much. And it's a pleasure to be with you today.